Here we have an op-amp circuit. Again, notice that we have a feedback loop here from the output to the inverting terminal, so we can assume that this op-amp is going to function in the linear region. We want to know what the output voltage is for the following values of Vs. So we're going to change the signal voltage here, this input voltage, and we want to know the output voltages. When I look at all these different values, I see a bunch of different values of Vs. I don't want to have to redo the calculations 6 different times here for these 6 different values. So what I want to do instead is come up with an algebraic relationship between V0 and Vs. If I can come up with one equation that relates these two values algebraically, then I can just plug in the individual numbers and get a value output for each one of them. If I want to know the range of Vs, this same algebraic equation that I come up with up here will probably help down there as well. So in this case, we have our op-amp. We see that we have a feedback loop to it, and so we're going to assume that this is operating in the linear region. That means that we should have the same voltage between our inverting and non-inverting terminals. They should be at the same voltage, and that the current going into each one should be 0. This non-inverting terminal is going to ground, and so then if this is ground, this is 0 volts, then this should be 0 volts as well, because again we're in the linear region, and so that means that we have 0 volts at this terminal here, and then indeed at this whole node should be at 0 volts. And so we're going to have a current flowing in from our signal, we're going to have a current flowing in from our output, and so we know that those two are flowing in the way that we've defined them. There's nothing flowing out, and so our KCL equation is thus. Then I can rewrite both of those currents in terms of the voltage differences and the resistances for each one. In this case, I'm going to multiply through by 80K. 80K times 0 is 0, that doesn't change. 80K and 80K cancel, and the 80K and the 16K cancel, and I get a factor of 5 left. 80 divided by 16 is going to be 5. So I have an algebraic equation relating VO and VS, and notice here I kind of skipped the step here when I plugged in numbers, but in fact what's going on is this equation that we find is just the equation for the amplification of an inverting amplifier circuit. 80 divided by 16 gives me 5. So now that I have a algebraic equation relating these two values, I can go ahead and plug in Vs, each one of these values of Vs, and I can get a output value V0 for each one of those. And so I've taken the 6 different values of Vs that we're looking for. We found that VO is actually -5 times Vs, and so I was able to find 6 different values of VO by taking the Vs and multiplying by -5 gives me VO, and the next value of Vs times -5 gives me the next value of VO, and so forth. But the last thing that we have to look at is that we have this relation here, but this equation assumes that our op-amp is acting in the linear region, which is assuming that the op-amp is not saturated. And that means that the assumption that this equation and all of these calculations only work if VO is between the supply voltages of the op-amp. And so when we're finding these values of VO, mathematically we get these numbers, but in real life there's a limitation on VO. And so we have to look at these values and make sure that they are between these source voltages. These are, so they're good. Negative 16.5 is lower than negative 15, so the output voltage really wouldn't make it to negative 16.5. The output voltage would get lower and lower until it hit negative 15, and then it would just stick at negative 15 because it would reach saturation and would stay at that value. If we have 3 and we have 8, those are fine. Again, those are in this range. But if the output voltage was trying to get to 12, that output voltage would hit 10, and the op-amp would reach saturation the other way, and so it would stay at 10 in that case. We would have gone out of the linear region into saturation, and so we have to correct these two values where our assumptions are incorrect. If we're looking for the range of Vs required to avoid saturation, well, to avoid saturation, we have this requirement here. We want the range of Vs that avoids saturation, and saturation depends on VO. So we need our relationship between VS and VO. One trick of inequalities is that if you divide through by a negative number, here we'll divide through by -5 to get VS by itself. If you divide by a negative number, you reverse the direction of the inequalities. So if I divide by -5 here and -5 there, -15 divided by -5 is 3. I reverse the direction of the inequality. +10 divided by -5 is a -2, and I've reversed the direction of the inequality. So here is my range of VS values that get amplified to be VO values, and then we want that VO values to stay in the saturation range. So we're able to put VO in its saturation range, then replace VO with the expression for VS, and then solve for VS. That gives us the range of VS.